Okay, here are the answers to the harder related range problem. So we got a camera located 50 feet from a straight road. So I'm going to draw a road up here, do my best to make it look like a road. There's those little marks that go down the middle of the road. And here's our camera right there. Camera's just going to be a box. I don't feel like drawing anything more. 50 feet away. So 50 feet away, when we're measuring distance, we go straight from one thing to another. So this is perpendicular right here. I'm even going to put that in, a little right angle right there. So this is 50 feet. And we've got a car on this road. I don't even want to attempt to draw a car, but I will. There's a couple wheels. You know, there's a car. That's a great car. And it's traveling, well, we're going to travel that way. Car traveling on this road at 100 feet per second. Now, this camera rotates here, you know, kind of spins around like it is right now, so that it's pointed at the car at all times. So we've got this line of sight here from the camera to the car. Okay, so this is making us a right triangle here. Now the question that is asked is in radians per second, how fast is the camera turning as the car passes closest to the camera? So we need to add the variable in here. We care about this angle. How fast is this angle changing? Because that'll tell us how fast the camera is turning. So I'm going to start adding some variables to my chart. Theta. That's the angle. Now, when the car is closest to the camera, so let's see if I can move my car here. Zoom, 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 zoom. There's the car. The camera is going to be turned right here. What's going to happen to this angle? Well, I can't move that one. Too bad. But do you get the idea? This was going to follow too. That angle is actually going to go down to 0. So theta is going to be 0 at that point. So theta is 0. Now I need a d theta dt. That is the rate of change of the angle over time. Well, that's what we're trying to find here. So I'm going to circle that one. D theta dt. What else do we have in this problem? Well, we have that the car is traveling at 100 feet per second. So I'm going to go ahead and call my two sides A and B. I'll call this side of the triangle B and this side A. So we have that d dt is, now think about it, is side B shrinking or is side B getting larger as this car travels? Right now it's getting smaller, so dB dt is negative 100, and B, that's the measure of that side. Remember, we care about this exactly when the car is closest to the camera. So the car is closest to the camera when it's right in front of it, so B is going to be 0 at that point. Okay, now do we know A? A is the distance from the camera to the road. That never changes. That's 50. And I think I just gave away the next part. dA dt is 0 because it never changes. Okay, so what sort of equation do we have that relates these things? We have an angle, and we have a couple sides, and we're in a right triangle, so that means we're going to be using sine, cosine, or tangent. So, hold up. People are trying to talk to me. Okay, I'm back from saving the world. Um, anyway, we need the equation that relates these three things, and that would be, oh, okay. Actually, I like to split my board like I do normally. Can I get it? Yeah. Come on, stuff. No, bad, bad. Don't do that. Move. There we go. So the equation that relates these things would be tangent of theta equals b over a. Tangent of theta equals b over a. Okay, I'm going to split my board up like I've done in every other problem here. And then down here in this space below, I'm going to take the derivative. Well, I don't want to use quotient rule. I like to avoid using quotient rule in problems when I don't have to. So I'm going to multiply the a over first. A tangent of theta equals b. Now I'm going to take the derivative. Now a is a function. Tangent of theta is another function with a function in it. I'm going to use my product rule here. So I've got dA dt times tangent of theta plus, and now A, the original first one, times, now tangent of theta, I've got to take the derivative of the outside. The derivative of tangent is secant squared. Plug in the inside, theta. Okay, running out of room. That seems to be my favorite thing to do when I do problems on the board. Secant of theta, so I took the derivative of the outside, secant squared, plugged in the inside, theta. Now I need to multiply by the derivative on the inside, d theta dt, then equals, and on the other side I have b, which just becomes db dt. All right, so I've got one, let's see how many variables. I've got one, dA dt, I've got one, theta, got another one, a, theta, I've already counted that, d theta dt and dB dt. 5 different variables there. And I want this one to stick around in the problem because that's what I'm trying to solve for. So do I have values to plug in for the rest of them? Yes, I have a dA dt. I look at my chart. Yes, I have a theta. Yes, I have an A. Yes, I have a dB dt. So I'm going to go ahead and plug those values in here into my problem. So dA dt, let's plug on in. dA dt becomes 0 times tangent of 0 plus, now A is 50 times secant squared of 0 times d theta dt equals, and dB dt is negative 100. Oh, my handwriting is getting bad down there. I need to scroll down. Okay, so I'm simplifying. Tangent of 0 is 0. So this is all 0. Plus 50 times secant squared of 0 is 1. So this is 50 d theta dt equals negative 100. And then I'm going to divide the 50 over. So I'm going to scroll down a little bit more. I'm going to get d theta dt equals negative 2 radians per minute. So that, now why is it negative? Why is it negative? That's kind of strange. So look back at our problem here. Think about theta as the car is moving here, as the car is going this way, is that angle, if this dotted line here goes straight to that car, if we get this new dotted line now to the car from there, is theta going to get bigger or smaller? It's going to shrink. So that's why d theta dt is smaller. Now, in order to answer the problem, it just says how fast is the camera turning. The problem simply says how fast is it turning. We would just say that the camera is turning at 2 radians per minute. The question didn't really have a directional component to which way is it turning. It wasn't about how fast is the angle shrinking, just how fast is it turning. So that's how we get 2 radians per minute. All right, on to the next one. Okay, as a spherical mothball evaporates, its volume decreases at a rate proportional to its surface area. So a quick word about what it means for 2 things to be proportional. Proportional. Here, I'll write the sentence. Y is proportional to X. Y is proportional to X. This sentence in words, what this means is Y equals KX for some constant K. So if 2 things are proportional, then they vary by a constant. So think of it this way. If I work at a job that I make $10 an hour, my weekly wage is proportional to the number of hours I work. Like if I work 2 hours, I get $20. If I work 10 hours, I get $100. If I work 8 hours, I get $80. It's always my wage equals 10 times my hours worked equals my wage would be my output equals some constant 10 times my hours worked. That's what proportional means. Okay, so we got to figure out what two things in this problem are proportional. Its volume decreases at a rate proportional, decreases at some rate. Well, what is that thing right there? That is dV dt. dV dt. The decrease of the volume, the rate at which it's decreasing is dV dt. The rate proportional to its surface area. Now, this isn't saying to the rate at which its surface area is changing. This is actually just the regular old surface area. Okay, so let me get equations for those things. We're working with a sphere here. So the dV dt, I think we've used the volume and surface area equations enough that we might know that dV dt is 4 pi r squared dr dt. And I'll put it up here where that comes from. V equals 4/3 pi r cubed. And we take the derivative of that, deriv, to get dV dt. This is dV dt. Where do I want to put that? That's fine. dV dt. So I got that. Now, surface area. Surface area. What does this equal? The surface area equation is 4 pi r squared. 4 pi r squared. So, so let's look at our problem. It says we're given that these two things, that dV dt right here, boom, and surface area are proportional. So let's set up that equation right here, this sort of proportion right here. Let's set up that equation between them. So dV dt, I'll write on the left-hand side here. dV dt is proportional to the surface area. dV dt is proportional to the surface area. And k is some constant here. Okay, let's substitute in. So dV dt, what goes in there is 4 pi r squared dr dt. And what goes in for surface area is 4 pi r squared. Okay, a little more space here. Now I divide both sides by 4 pi r squared, 4 pi r squared, and I get that dr dt equals k. And what assumptions did we make about k? We assumed that k is a constant. This is a constant. We had to assume that to set up the proportion. So k is a constant. We've shown that dr dt is a constant. That means we have shown that the rate of decrease of the radius is constant. The dr dt, the rate of change of the radius, is constant. All right, quick pause for me here. All right, on to the next one here. Okay, a man starts walking eastward at 5 feet per second from point A. Okay, let's put a point A up here. Here's point A. The man's going this way at 5 feet per second. So I'm going to add that into my picture just in a way that makes sense to me, that this guy is moving this way at 5 feet per second. 10 minutes later, a second man starts walking west at the rate of 5 feet per second from a point B, which is 3,000 feet north of point A. So I'm going to put B up here and draw this line in. This is 3,000 feet. And man B here, I just call him man B since he starts from point B. He's walking west, so he's walking in the opposite direction here. Dot, 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 dot. Oh, those dotted lines didn't match up. Dot, 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 at 5 feet per second this way. 5 feet per second. Okay, how fast are they separating 10 minutes after the second man starts? So 10 minutes after the second man starts, what else can we figure out in our picture? Well, we can figure out how far these people have traveled. We know how fast they're walking, and we know exactly how long they walked for. So man A here, I'll put him in red. Man A went 5 feet per second for 20 minutes. For 20 minutes. So that's, let's convert this to the 5 feet per second. That's times 60 seconds in a minute. So that would give us 1 minute times 20 minutes. I think that makes sense. 5 feet per second times 60 seconds in a minute times 20 minutes gives us that man A traveled 6,000 feet there. So this side is going to be 6,000 feet long. 6,000 feet long. Now, man B actually walked the same rate and exactly the same rate for exactly half the time, so I don't know why I'm bothering to do this computation. I bet you can figure it out. 5 feet per second times 60 seconds to get to 1 minute, and then he went for 10 minutes, and this gives us 3,000 feet. So he went 3,000 feet in this direction. 3,000 feet. Okay, this is what we have. This is my real setup and my picture right here. Now I look at my question. How fast are they separating? How fast are they separating? Well, man B is right here. Smartboard needs a line. Is right here. And man A is right there. The distance between them is this right here. This blue dotted line is the distance between them. And we want to figure out how fast they're going apart here. Now, instead of going ahead and just looking at this as two triangles, we can make it one triangle because we don't know the things in each individual triangle. So just play along with me for a second. We don't know this distance. We know that the whole thing is going to be 3,000 feet, but we don't have a way to figure out that distance. We actually know very little information in this triangle right here itself. We can't figure out the hypotenuse. We can't figure out that vertical leg. We can't figure out any of the other rate of changes. So that triangle is of very little use to us. Instead, let's look at this triangle right here. Let's look at this triangle right here. That triangle is something we can work with. We can work with that triangle. I'm going to get rid of these calculations of how long the sides are real quick. Let's group these and throw them somewhere useful for posterity's sake. I'll throw them up here. Okay, this triangle right here, I'm going to pull it off of the picture now and put it right down here. Yeah, I'm going to put it down here. Okay, so it matches up. Let's label some sides on this triangle. Now this bottom here is the bottom of our big triangle is made up of both of the horizontal segments. That's this segment and this segment in our upper picture. So the bottom here is 9,000 feet long. And the vertical part of our triangle is the exact same length as this middle segment, the vertical length. So that is 3,000 feet long. And we want to know, and let's give this side a name. Let's call it C. And I'm going to start making a list of variables up here. Hopefully I have enough room. So I'm going to call this bottom side A, this one B. So I know that I'll go in a little different order here. I know that C is, I don't know that yet. So I don't know. And dc dt, the rate of change of C with respect to time, well, that's what we're trying to find here. So I'm going to circle that. I know that B is 3,000. So dB dt is the rate of change of that. Now think of where this 3,000 here came from. It came from right up here, the distance from A to B. That ain't changing. So dB dt is 0. Now A is 9,000. and dA dt, the rate of change of A over time. Think about it. How is it, where did A come from? A came from this guy's distance and this guy's distance. So what's going on? This guy's walking 5 feet per second that way to the left. This guy's walking 5 feet per second to the right. So this side right here is increasing at a rate of 10 feet per second because they're each adding 5 feet onto it per second. Okay, so we've got some values here. Now we can even get one more value. Let me run and grab my calculator. Okay, I got my calculator because I know I've got a right triangle here. Why not? Let's just get C real quick. I don't even know if it's going to be useful to us, but we can do it, so why not? 9,000 squared plus 3,000 squared equals C squared. So let's type that in. 9,000 squared plus 3,000 squared is a really big number. And so C squared equals 9. How many zeros is that? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And the square root of that, square root of the answer, oof, C equals 3,000 square root 10. 3,000 square root 10. That's the simplified version of it. Okay, so I've sort of given away the formula we're going to use here. Hopefully, you see the formula that relates all the things we know, which now we know everything in that chart, and only has one thing we don't know, dc dt. It's the Pythagorean theorem. So I'm going to put that down here. A squared plus b squared equals c squared. I'm going to take the derivative of it, 2a dA dt plus 2b dB. That's a B, yep, I believe it too. dB dt equals 2c dc dt. Now I'm going to plug in things from my chart. So I have some values here. Let's see, I'll stick with green. 2 times A is 9,000. dA dt is 10. Plus 2 times B is 3,000. 2 times 3,000. And dB dt is 0 equals, oh, doing my favorite thing again, running out of space. Move it on over. Okay, equals 2, and C is 3,000 square root 10. And dc dt, well, that's what we're trying to solve for, so that stays in our problem, dc dt. Okay, time to simplify. Alrighty, so this one goes away, times 0. Get rid of that thing. This first one, 10 times 9,000, that's going to add a 0 on it. Times 2 is going to make it an 18 out front. So this becomes 18, 1, 2, 3, 4 zeros, equals 6,000 square root 10 dc dt. Okay, divide it over, so I've got 18,000 divided by 6,000 square root 10 equals dc dt. Now, we go ahead and simplify. We can simplify, first of all, with factors of 10. So there's a factor of 10, a factor of 10. There's another one. There's another one. 6 and 18. That's, yep, that's going to become 3 and 1. So I'm end up here with, this is really, I promise, all this simplifying is really, it really does work, even though it seems like I'm kind of cheating here. As 30 over square root of 10 equals dc dt. I think it all works at least. 6 times 30. Yep, I think that all works. 30 over square root of 10 equals dc dt. Now, what did I have on the answer to? Let me check. I'm going to pause it real quick and check. Okay. Yep, this is going to work out. We're good to go here. Let's finish it off. 30 over square root of 10. Now, you may have learned in your Algebra 2 class that for some odd reason, back in the olden days, we hated having square roots in the denominator, so we would always multiply by the square root on the top and the bottom in order to get rid of it. So we would end up with 30 square root of 10 over 10 is dt, and this would become 3 square root of 10 is dt, which is the most simplified version, even better than what was on the answer key that I had up in class. Now, what is this unit, dc dt? Let's look back in our problem. So it's the rate of change of that distance. We were being measured in feet, and I think we did everything in per second. So this is a measurement of feet per second. 3 square root of 10 feet per second. I'll just throw it over here. 3 root 10 feet per second. All right, very good. On to the next one. A ladder 13 feet long is leaning against the side of a building. Here, I'll draw it over here. Here's my ladder. It's 13 feet long, leaning against the side of the building. The foot of the ladder is being pulled away from the building at a rate of 8 inches per second. Right away, some alarm bells should go off in your head because the ladder was 13 feet long. And now the base of the ladder, here, I'll draw my building in here. I never draw fancy buildings. The base of the ladder is being pulled away at 8 inches per second when the ladder was 13 feet long. So I'm going to convert this 8 inches per second to, I believe that's 2/3 feet per second, right? Because 8 out of 12 is 4, 8, 12. Yep, 2/3 feet per second. It's moving away. How fast is the area of the triangle formed by the ladder, the building, and the ground changing at the instant when the top of the ladder is 12 feet above the ground? So we're given this as well. Okay. Now, so we want to know about how fast is the area changing. I want to know dA dt. That's the one thing I don't know. Well, probably not the one thing I don't know, but that's for sure one of the things I don't know. Want to know dA dt. So we also have to have A. We don't have that yet. Let's go ahead and do A, B, and C for our sides. There's A, there's B, there's C. So we've got that A equals, well, I don't know that. I wasn't given that in the problem. dA dt, dA dt. Oh, I'm going to continue on using a lowercase and an uppercase a in this problem. You might find it a little bit confusing, but it's actually not that uncommon in mathematics to use the same letter, lowercase and uppercase, to represent two different things. Okay, dA dt is 2/3 because I converted everything to feet. And then B is 12. And dB dt is, well, don't know that one. I don't know how fast it's sliding down. And C is 13, and dC dt is 0 because the ladder is not changing. It's not an extendo ladder or a shrinko ladder. I don't even know if those are real things. That just sounded cool. So we're trying to find dA dt. So we need a formula that's going to get us a dA dt. So we gosh dang better set up the area formula. Area equals 1/2 times base times height, but in this case, times lowercase a times b, because those are the variables I'm using. And I'm going to go ahead and I guess I'll divide up my screen since I did this one so nicely. Divide it up here and here. I'm going to go ahead and take the derivative of this because I need a dA dt. So dA dt equals 1/2. That's a constant multiple. Then I do the product rule. A dB dt plus B dA dt. Okay, now What of these variables are okay to be here? dA dt. That one's okay to stick around because that's the one I want to solve for. A, do I have a value for that? No, that's a, we don't know. I'm going to put a red squiggly. No, I don't like the red squiggly. What can we do? We'll just put a triple underline there. Triple underline. We don't know about that one. dB dt. Do I have a value for that? Oh gosh, I don't have one for that either. Ah, there's going to be a lot of work to do. B, I do have a value for that, so I'll just put a single underline. That one's good to go. The ADT, I do have a value for that. All right, so now we got to use our tools, use our picture, use our brains, use any other equations we can think of, or the equation we already have, to find some of this stuff. Now, if you'll notice, the reason that I go straight to doing the area formula and dA dt and then figure out stuff is this capital A, the actual area. Is that anywhere in here? Nope. So we might not even need to find that. So why waste the extra time? Okay, I'm going to start by finding A because that one's pretty straightforward. I can find A by using, let's go with blue here, A squared plus B squared equals C squared. A squared plus 12 squared equals 13 squared. And this is one of those Pythagorean triplets that appear quite frequently, a set of three integers that work in the Pythagorean equation, formula, whatever. And then A is going to be 5. So I've got A now, so I'm gonna check mark under that. Yep, got A. Now I need dB dt. Look at all the stuff I've got. I've got A, B, and C. I've got dA dt and dC dt. I'm going to go ahead and use this Pythagorean equation again to get dB dt. So it's A squared plus B squared. I'm going to draw a line here. B squared equals C squared equals C squared. I'm going to take the derivative, 2A dA dt plus 2b dB dt equals 2c dc dt. Okay, now I have values to plug in for everything except for dB dt, because that's what I'm trying to solve for. Let me scroll up a little bit to my chart. So dA dt is 2/3. I'll try and get them both on the same page. Okay, gotta get, nope, not gonna be able to plug in. dA dt is 2/3, dC dt is 0. So I'll plug in a bit at a time. 2/3, dC dt is 0. Let's look at our sides now. A was 5, B is 12, C is 13. A was 5, B was 12, C was 13. Okay, hopefully I have enough space here. dB dt, 2, a 2, a plus sign, and a 2. That's a 2 times 5. There we go. Okay, now this side opposite the equal sign goes to 0, and I just do some combining here. 2 times 5 is 20, or 10, times 2 is 20. So this first thing becomes 20/3. 20/3 plus 24 dB dt equals 0. I subtract my 20/3 and I get 24 dB dt equals negative 20 over 3, not 4, 3. And then I divide each side by 24 or multiply by 1 over 24. So dB dt equals negative 20 over 60, 72. 72 equals negative 10 over 35, 36 equals negative 5 over 18. I think that simplifying works. Yep, that simplifying works down to negative 5 over 18. And then finally, I can go back and plug in. I can put a, actually, I want to put my check mark here first. Check, got dB dt. Now I can plug everything into this dA dt formula. There's going to be a lot of scrolling up and down as I try to get all my variables in here. So I'll rewrite my formula here. So dA dt, dA dt is 1/2. I'm going to put it in the same order as it was before. A dB dt plus B dA dt. Okay, let's plug in. dA dt equals 1/2. A is 5. dB dt is -5/18 plus B is 12. And dA dt, I think it was 2/3, but I'm going to scroll up just to make sure. Yes, 2/3 times 2/3. Gosh, there's a lot of fractions in here. Okay, let's figure this out. Scroll down, equals 1/2 times, this is -25/18 plus this is 24/3. Okay, so I can actually convert this fraction, the second fraction, to be over 18. Let's do that so we can combine them. This is going to multiply by 6 on the top and on the bottom, and it's going to become 144. 144/6. So I'm going to, when I combine them, get 1/2 times. Now, if you just use your calculator at this point, that'd be more than okay. But sometimes it's good to exercise those mental math skills. 144, and then we're going to subtract 25. So I believe that is 119. Yep, over 18. Yeah. I got to change that. It's not 144/6. It's 144. We were multiplying by 6, so it's 144/18. Okay, so this becomes 119/36. And here's the point where I pause the video and cross my fingers that I did it right. Look, I came back showing the answer key so you could see that I did it right. It's 119/36. That's dA dt. And the question asked for us to do it in feet squared per second, and we already converted everything into feet. So I'm just going to go ahead and add my units here. Feet squared per second. Good to go. Awesome. Okay, going to take a quick pause here. All right, one more problem, I believe, right? Just one more? Yep. One last problem here. Okay, a particle is moving around this ellipse. Now, if you know anything about ellipses, actually, I don't remember anything, even though I teach algebra 2. Well, I know they look like that. I can't remember whether this one would be oblong this way or the other way, but we've got a particle going around this ellipse. At any time t, its x and y coordinates are given by these two, these are parametric equations. If we could put them in, we could graph this ellipse. So a little throwback to your pre-calc days. So let's put a random point here on the ellipse. There's a random point, and its coordinates are this: 4 cosine t, comma 2 sine t. That's the coordinates of that point. Now, at what rate is the particle's distance to the point 2, 0? I'm going to throw 2, 0 on here. There's 2, 0 right there, 2, 0. At what rate is the particle's distance to the point 2, 0 changing at any time t and when t equals pi/4? So we got to do the general case in order to do the specific case. We got to do the anytime t first. So distance between them, that's right here, the distance from here to here. Now we're talking about points. We're on a coordinate plane here. Hopefully you got the idea that there's a formula that has to do with distance. It's called the distance formula. So we're just going to be using that. It's a distance equals square root of y2 minus y1 squared plus x2 minus x1 squared. Distance is the distance formula is actually just a is the Pythagorean theorem here, but that's for a different day. Actually, that's for an algebra 2 class. So the x2 and x1 coordinates are going to come from our x coordinates of these 2 points. The y coordinates are going to come from our y coordinates of these 2 points. And we're just going to go ahead and plug right in because we want, I'll even write this up here, we want d, let's call it, let's say distance, nope, I've already used little lowercase d down here, so dt. That's what we want to find. So let's plug on in. Distance, well, I don't know the distance yet. So d equals square root of, I'm going to use my complicated point as my first one, or as my like y2 and x2. So we've got 2 sine t minus 0 squared plus, and then 4 cosine t minus 2 squared. All of that under the square root. Now, when we want dt and we have this thing, we're going to need to take the derivative. I'm going to save myself a little work by getting the square root out of here, by squaring both sides and going back to what looks like the Pythagorean theorem, because that's what it is. Going back to d squared equals, now this is 2 sine t squared plus 4 cosine of t minus 2 quantity squared. Now, before I take the derivative, I'm even going to do a little more simplifying. This first one right here, I don't want to use the chain rule for that. So I'm going to actually square it and get 4 sine of t. I guess I'm still going to have to use the chain rule. Whatever, let's just not do that then. Whatever. We'll figure it out one way or another. Okay, let's take the derivative. Just go ahead and do it. 2d and dd dt equals, now here we've got to do the chain rule, so 2 times the whole, or yep, plug in the whole inside here, 2 sine of t, and then I need to multiply by the derivative of the inside, which remember, I'm taking the derivative with respect to time, so this just becomes, I don't need this one, this becomes times 2 cosine of t, and then plus, and this one I'm going to have to do the chain rule. Maybe I should give myself a little more space already. Group these together, make them a little smaller. Okay, this one becomes derivative of the outside is bring down the 2, plug in the whole inside, 4 cosine of t minus 2, and then times the derivative of the inside times 4, well, let's be smart with our negatives, times negative 4 sine of t. Okay, there's my whole derivative. Now, the question was, what is dt at a random time t? So right now, you see our thing has a bunch of t's in it. We're allowed to have t in it. It wants, the question here, I'll go back up to the top here. The question, what rate is the particle's distance to the point changing at any time t, means that we want dd dt to be a function of t. So we want dd dt equals, and then a whole bunch of stuff with t. However, we have one little problem here, and it's that we have this 2d in there. So we're going to need to deal with that here in a second. So we need to deal with that. First of all, I'm going to get it over to the other side. Man, I want to do some cloning here. Let's do some ungrouping. This is where I get out of a little bit of work, because I'm going to copy and paste. And wowzers, I've got this. So now dd dt, I'll go ahead and write that. I can be bothered to do that. dd dt equals this all divided by to d, which is great all and dandy, except for the fact that our equation for dt now has a d in it. So how are we going to get everything in terms of t? Yep, you're entirely right. We're going to have to plug back in this right here. This is d equals and a whole bunch of stuff to do with t. All right, this is where copy and paste comes in handy. So I'm going to copy all of this and paste it, move it down here. And I'm going to get rid of my 2d on the bottom because I don't want 2d down there anymore. I want 2 times, I'm going to plug in for d, so it should be square root of 2 sine of t squared plus 4 cosine of t minus 2 squared. 4 cosine of t minus 2 squared. Okay, this is it. This is really it. I guess you could do a little more simplifying. Let's go ahead and do this. We've gone this far. Why not go to the last final step? dd, dt on the top. Let's simplify our first term. I've got a 2 times a 2 times a 2. 2, 4, 8. So it becomes 8 sine of t, cosine of t, plus, and in this term, oh, okay, I can distribute here, plus 8 cosine of t, and then minus, or shoot, am I missing something? Yeah. It's not plus 8 cosine of t. Man, this is the problem when you don't use parentheses. Even myself, when I don't use parentheses everywhere I should, I get myself in a little trouble. It's going to be plus 8 because the parentheses that I probably need here is maybe around this thing to show that this also needs to get distributed as well as this 2. Okay, both of these things need to get distributed into that thing right there. So I'm going to erase those real quick and do it. Actually, I'm going to leave those parentheses in. So distributing to the first term becomes 2 times 4 cosine of t becomes 8 cosine of t. And then I'm multiplying by negative 4. So it's going to become negative 32 sine of t cosine of t, sine of t cosine of t, negative 32 sine of t cosine of t, and then I'm going to make everything a little bit smaller so I can fit the last term. Actually, it's really good that we're doing this simplifying because we're going to get some canceling out, as you can see right now. Group, and small. Okay, now we're going to distribute the 2 to the minus 2 and the negative 4 sine t to the minus 2. So that's going to become positive. Oh, I don't want green. Picked up the wrong pen. It's going to become positive 16 sine of t. Okay, and then all over that same stuff on the bottom. All over that same stuff. And we're going to simplify a little more. dd dt equals 8. We have sine t, cosine t. We got 8 of them, and we're taking away 32. So this is negative 24 sine of t cosine of t plus 16 sine of t. See how things are getting so much simpler? Yeah, and I'm going to take this bottom part, bring it down here, be my denominator. And there's one last pretty straightforward simplification I'm going to do here, is that I can take a 2 out of every term, can divide everything out by 2. So dd dt equals, this is negative 12 sine of t cosine of t plus 8 sine of t all over. Now this on the bottom, since it's 2 times this whole thing, this is all one term. So just that 2 goes away. So I got to just grab all of the other junk. All of this. Okay, so that's dd dt. Hopefully, to be honest, that one wasn't in my answer key. I trust my work, but I wouldn't be surprised if I made a mistake along the way. Feel free to point it out to me if you notice my mistake. Now, for plugging in pi over 4, I'm going to spare you the problems of having to watch me do that, and I'm just going to go right here and snip the answer right off my answer key and throw it in there. I'm sure you can figure out how to plug in and evaluate all of that. And I would be using my calculator, or if I was especially a good student and had all my special trig values memorized, I would use that. So this is dd dt when t equals dd dt when t equals, was it pi over 4? I have to scroll all the way back up. Pi over 4 equals pi over 4. All right, so that's going to conclude everything for today. Now, this last problem, yes, this one is insane. Would I ever put a problem quite this crazy on a test? No, probably not. Is it good to know how to do and to work your way through these problems? Yes, for sure. Some of these problems today, I know they were a little different, a little more difficult. Hopefully, you got to exercise your brain a little bit and see how you can apply related rates to a lot of different formulas or setups. I think they're pretty cool problems. Hope you have a good rest of your day.